Welcome back, everybody. In section 7.2, we're going to be working on estimating the population mean. In section 7.1, we were working on finding confidence intervals for a proportion. In this section, we're doing a very similar thing, coming up with confidence intervals, but this time instead of trying to estimate P, we're trying to estimate mu. So you'll see a lot of parallel in this section between this section and what we did in the last. So first thing is the idea of a point estimate. So we had before the idea that P hat was a good estimate of P, and so it makes sense that X bar is a pretty good estimate of mu. So X bar is the best point estimate of mu. Okay. One of the other new things for this section is that we're going to have another distribution table. We used a lot of the Z table in the last section. We'll have a new table called the T distribution table in this section. So I sent you a copy of that via email. It's also posted on Canvas for your reference. If you can, you should print one out. If you have a paper copy of the textbook, it's probably in the back of the textbook. So the T distribution, the formula basically for it is T is X bar minus mu over S over square root N. And so the easiest way to think of that, I think, is to compare it to the Z distribution, where it was X bar minus mu, that part's the same, and it was divided by sigma over the square root of N. So the real difference between Z and T is the S versus sigma. In T, there is an S in the formula. In Z, there is a sigma in the formula. And basically, it is what is going to end up differentiating which table you use is whether or not you know sigma. In a lot of real cases, you don't really know what the population standard deviation is going to be. And so you're going to end up using a T distribution. Okay. So a concept that is new for the T distribution that we didn't have for the Z distribution is the idea of degrees of freedom. The T distribution depends on, and which values you end up looking in the table, depend on the sample size, and that's related to the degrees of freedom. As part of calculating the confidence interval and doing other tasks, we'll have a critical value, T alpha over 2. We had a Z alpha over 2 in the last section. And we're going to need this idea of degrees of freedom. And basically, I'll leave you to read the paragraph there. But the degrees of freedom is always one less than what the sample size is. And this also has to do with the kind of why this formula for standard deviation in chapter 3 had an n-1 in it. It was related to this idea of degrees of freedom. So remember that degrees of freedom, when you look in the table, is always n-1, where n is the sample size. So we want to get some practice at looking at the table. Before we do that, though, we want to think about some different properties of the T distribution. The distribution is different for different sample sizes. So there's a picture shown here. The T distribution is kind of bell-shaped like the normal distribution, but not exactly the same. In the picture here, there's a blue standard normal distribution, like we would have had in 7.1 off of our Z table. And then there's a red T distribution with an N of 12 and a kind of yellow T distribution with an N of 3. If the bigger that N is, the closer the T distribution will match our normal distribution. Okay, so the T distribution has the same general bell shape as the normal distribution, but has more variability. As we would expect with small samples. Small samples are going to be more variable than large samples will be, and that accounts for why at the ends of the distribution, the tails are fatter. So there's that. There's a mean of 0, and just like the standard Z table had a mean of 0 as well. The standard deviation for the T distribution varies with the sample size. With the normal distribution, the standard deviation was 1. For the t-distribution, it's going to be greater than 1, but it depends on what the sample size is. As the sample size n gets larger, the t-distribution gets closer to the standard normal distribution. All right, so the book has some directions on which, or criteria telling you when you should use which distribution. That's this table 7.1 shown here. I'll leave it to you to really look at this. I think that the directions here were kind of confusing because they repeated some information here about like n being greater than 30 and so forth. So I'd recommend using this flow chart off the notes right here. So there's basically a couple of questions you need to ask yourself. Do you know that the population is normally distributed, or is your sample size bigger than 30? If the answers to both of those questions are no, then you need to use something called non-parametric methods, which are in chapter 13, or bootstrapping method. Again, basically stuff that is later in the book. If you have the property that the distribution is normal, or the sample size is bigger than 30, we're going to take the right branch of our flowchart. Then you ask yourself, do I know sigma? Do I know the population standard deviation? If you know the sigma, then use the z-table. If you don't know the population standard deviation, which is true for a lot of realistic cases, if you don't know the sigma, then you're going to use t. So most of the time in this class, you ask yourself, do I know sigma or not? If you know sigma, use z. If you don't know sigma, use t. And in a way that makes sense if you go back to the formula that we'd had. In the z formula, it had a sigma in it. If you know sigma, you can use z. The t formula has an s in it. So you would be using the sample standard deviation where you don't know the population standard deviation. All right, so first or next thing we want to do is practice at reading the table. And the structure of the t-table is different from the t-table in a couple of ways. As I'd mentioned, for one thing, it depends on something called degrees of freedom, which is 1 less than the sample size. The other kind of big difference in this table versus the z-table is that the z-table had basically cutoffs on the margins of the table, and the middle of the table was areas. This one, it's backwards. Along the top row of the All right, so now let's try this. Here it says a sample of size 15 is a simple random sample from a normally distributed population. So the sample size is just 15, but we know the population is normal, so it's okay. We're going to use t. We're to find the critical value t alpha over 2 corresponding to a 95% confidence interval. So we're going to get ready to do a 95% confidence interval. So as always, a picture will help you. If we're going to do a 95% confidence interval, that means that 95% of the area is between two cutoffs. So what's left is 5% of the data taken in two parts, we'll have to have 2.5% on either side. In this example, the sample size is 15. Remember that the degrees of freedom is always one less. Degrees of freedom will be 15 minus 1 or 14. So we'll be looking in row 14. So that's row 14 because the sample size was 15. We always go one less. The area in two tails was 0.05. Area in two tails, 0.05. Notice that that corresponds to area in one tail being 0.025. It's just half as much. So where those two intersect is at 2.145. So we went down the rows corresponding to degrees of freedom, and the column came from what confidence level we had. We had 95% confident, so 5% is in two tails. Where those two met is 2.145. And so what is in the body of the table is the cutoff. So this will be 2.145. And then using symmetry, the other one will be negative 2.145. So unlike the Z distribution, what you're finding in the body of the table is cutoffs, is critical values. Okay, so let's try that again. So here it says a sample of size 8 is a simple random sample from a size 8 is a simple random sample from a normally distributed population. We want to find the critical value T alpha over 2 corresponding to a 99% confidence interval. So again, a picture will help. So we want to be 99% confident. So that means the area in two tails will be 0.01, 0.005 in each tail, or 0.01 in the two tails. Our degrees of freedom is going to be 7. So looking back at our table, degrees of freedom 7, 0.01 the area in two tails. Area in two tails is supposed to be 0.01. So that's the first column. Our degrees of freedom was 7. So we'll go down to row 7. And where those two meet, 3.499. So our cutoffs are at 3.499 and negative 3.499. Our T 0.005 is going to be 3.49. Okay, so now we're ready to try to find a confidence interval for mu. So the fine print from the book. Here, this is going to be the process for where we don't know sigma, which is the more realistic case. The players, the mu is the population mean, x bar the sample mean, n is the sample size, e, capital E will be the margin of error. Our requirements, we need to have a simple random sample. We need to have population either being normal or sample size being bigger than 30. The formula for the confidence interval, you'll notice that this is really similar in structure to what we had for proportions. We would have had, let's just do the first one here, p hat minus e is less than p is less than p hat plus e for the proportion. We had a way of writing it using plus or minus or using interval notation back in section 7.1. The big thing we're going to need is our expression for E. So this is our E. It will be the T alpha over 2 that we were finding a minute ago, multiplied by S over the square root of N. So yesterday or last time, for proportions, it was Z alpha over 2 times the square root of P hat Q hat over N. So this bears some resemblance. It has a T alpha over 2 instead of a Z alpha over 2. The denominator here has a square root of n. Our difference is that the standard deviation S we're going to use today is where the P hat Q hat square root would have been in the past. All right, so let's try an example. So here it says it's about mercury in sushi. Listed below are the amounts of mercury in parts per million found in tuna sushi sampled at different stores in New York City. The study was sponsored by the New York Times, and the stores in order, they list all the names of the stores, were given the sample mean and the sample standard deviation. We're to construct a 90% confidence interval estimate of the mean amount of mercury in the population. Okay, so in here, the standard deviation that we're given is the sample standard deviation, okay? So we don't have sigma. Since we don't have sigma, we're going to use T. Okay, so then we'll start with our T alpha over 2, which we'll need to get. We're going to make a 90% confidence interval. That means that the area in two tails is going to have to be 0.10. Our degrees of freedom, there were 1, 2, 3, 4, 5, 6, 7 stores. So degrees of freedom is going to be 6. Okay. And so we'll need to look up the value in our table. So let me get that. All right, so taking a look in our T table, our degrees of freedom was 6. And our area in two tails was 0.10. I didn't grab the right column. Let me go get that. All right, so that's better. So we want the degrees of freedom to be 6. And the area in two tails to be 0.10, so that's the last column here. So where those will intersect is at 1.943. So that will be our T alpha over 2. So then for our margin of error, it's T alpha over 2 times S over root n. Our T alpha over 2 was 1.943. Our standard deviation, we're told, is 0.366. And then square root of n. Here, be careful, we're not using the degrees of freedom here, we're using the actual n, which is 7. Okay, so let's calculate. So 0.102. So the sample mean was 0.719 plus or minus our margin of error, 0.102. 0.617. And then we'll add to get the other end, 0.821. All right, so what we've got then is a confidence interval for the mean amount of mercury in these sushis. So we could say that we're 90% confident that our interval 0.617 up to 0.821 contains mu. All right, so let's try another example. In this one, we're looking at the effectiveness of an Atkins weight loss program. Here it says, in a test of weight loss programs, 40 adults used this program. After 12 months, their mean weight loss was found to be 2.1 pounds with a standard deviation of 4.8 pounds. We're to construct a 90% confidence interval estimate of the mean weight loss for all such subjects. Then we want to decide if it's effective and then decide if it's practical. So what we'll do first is decide if we should be using Z or T and go from there. So it doesn't say anything about the distribution being normal, but we do know that there are 40 adults being tested, which is bigger than 30. So we're okay with either Z or T. We're not going to have to do chapter 13 yet. So do we know standard deviation of the population? It doesn't look like it. So the part here in the second sentence where it says after 12 months, their mean weight loss was found to be 2.1 pounds with a standard deviation of 4.8 pounds. It should be clear that that 4.8 pounds is the standard deviation of the sample, not the population. So we're going to be using T for this one also. So I'm going to start with a little picture. We again want a 90% confidence interval. That means we'll have 0.10 is the area in the tails. And then the degrees of freedom is going to be what? There were 40 adults, so it will be 39. So let's get out our table and take a look and see what that cutoff will be. All right, so we have a degrees of freedom of 39, one less than our sample size. And the area in two tails is 0.10, so we'll be in the fourth column. Where those two intersect looks like 1.685. So now we have our margin of error, which will be T alpha over 2 times S over root N, 1.685 times the sample standard deviation, which was 4.8 pounds. And that is divided by the square root of 40, which was our sample size. So that's 1.28. So then our mean was 2.1 pounds. So we'll take the sample mean plus or minus that E we calculated to produce the confidence interval. So 2.1 minus 1.28 and 2.1 plus 1.28. All right, so it looks like our interval is 0.82 up to 3.38. So the rest of the question, does it appear to be effective? To me, it does look like it appears to be effective because we're 90% confident that our interval doesn't contain 0 or negative values. So it looks like the mean loss is greater than 0, so people lost something, it looks like. It doesn't look like it's that practical, though, because losing about 2 pounds or so, 2 to 3 pounds in 12 months, right, is not that big of a deal, right? So that's the end of our example. All right, so I wanted to show you how to do the Atkins problem using StatCrunch. So I've signed into StatCrunch here, and to get a confidence interval for the mean, we'll go to Stat. And then we know we're going to end up using the t-distribution on this one, so go down to t-stats. At this point, we have only one sample. We're going to use the summary information. So our sample mean was 2.1. Our sample standard deviation was 4.8. and our sample size was 40. And then click the radio button to get confidence interval, and you'll want to change that to 90. We wanted a 90% confidence interval. Click on compute, and there we have it. The lower limit was 0.821, and the upper limit was 3.37. All right, so one of the other activities we had done in 7.1 was sample size, coming up with a size of a sample in order to estimate the proportion to a desired level of confidence and margin of error. We're going to do the same thing for the mean. So we're not going to derive the formula for this, we're just going to kind of be given it. So the formula goes like this. The sigma, of course, population mean, mu population mean, sigma population standard deviation, x bar the sample mean. And then the formula for it is going to be n, and then it'll be z alpha over 2 times sigma over e, and that's all squared. So in this, we will be using z, our standard normal table. It gives us a more conservative estimate than if we had used t. Additionally, if we don't have our sample size yet, we wouldn't have a way of saying what the degrees of freedom is anyways. Okay. If the sample size we get is not a whole number, always round up. Don't round to the nearest. Okay. So the formula here, just so you know, requires the sigma, but usually we don't have that. Usually we don't have the sigma. So if you're going to be figuring out sample size, then how do you work around that? So one way is to use the range rule of thumb to estimate the standard deviation. So we had seen in the past that sigma was approximately the range divided by 4. That would be one way of doing it. You could start the sample collection process not knowing the sigma, and then using the first couple values, calculate S and use S in place of sigma. And then as you obtain more data, you can revise that estimate of sigma and use that to revise your value of n. Or you could estimate the value of sigma by using the results from some other earlier study. All right, so an example says research of selling prices for 2-year-old Corvettes reveals that they have a standard deviation of 2,157. We want to know how many selling prices you would need to obtain in order to estimate the mean selling price of these cars, assuming that you want a 98% confidence, so that your sample mean is within $250 of the population mean. So our margin of error is 250. We're going to need the z alpha over 2. So I'm going to get that from the picture. We want it to be 98% confident. So that means that 2% is in the 2 tails, or 1% is in each tail. So then 99% of the data is to the left of our cutoff. So for this one, we will need to go back to our z table and locate in the body of the table 0.99. See what's closest. It looks like 2.33. Here, remember, we're using the z table for sample size. Okay, so then our n is everything squared. It's z alpha over 2, sigma over e on the inside. So everything squared, the z alpha over 2, which was our 2.33, times the sigma. We're told that the standard deviation was 2,157. And then our margin of error, we wanted to be within $250 of the mean. So let's calculate. Okay, so I'm getting 404.14. And with this, we should always round up. So we'll get 405. Sample size. Okay. Usually we don't know the sigma when we're finding a confidence interval. In case you do happen to know it somehow, the procedure for finding confidence interval is really similar to what we did before, like with the Atkins problem. What's different is that for E, you're going to use Z alpha over 2 instead of T alpha over 2. And of course, you'll use the sigma if you have it instead of using S. So when you know sigma, use the Z table. If you don't, use T. So let's try. This is basically back to the same sushi problem again. And all the values are the same here. The only difference here is that we're going to assume that the sigma is known to be 3.6 parts per million. So where we'll start as before is going to be with our picture. We're going to get a 90% confidence interval. That means that we have 10% of the data in the two tails, or 5% of the data in each tail, or 95% of the data is to the left of that cutoff on the right. And that 0.95 is 1.645. Okay, so here, notice we are using Z because we know sigma. So I'm using a standard normal table to get this 1.645, and we don't need to talk about the degrees of freedom or anything. Okay, so then margin of error. Is going to be our 1.645. Our sigma is assumed to be 0.366, and we still need our sample size, which was 7. So that's 0.228. So then the sample mean was 0.719, and we'll take plus or minus 0.228. So 0.491 up to 0.947. Okay, so that will be our confidence interval for mu, given that we know sigma somehow to be 0.366. All right, so I've added here the StatCrunch output, and also I wanted to let you know that I had to correct the version that we had done using the t-distribution. So the version you saw in the video is incorrect from a few minutes ago, but the notes posted on Canvas will be correct. So in here, notice that when we use the t-distribution, our interval, its lower end was 0.451. With z, the lower end was 0.491. With t, the upper end was 0.987. With z, it was 0.947. So the point here is that having sigma enabled us to produce a narrower interval. If we have a narrower interval, that means that we have a better sense of what our mu is. All right, so 2 more examples and then we're done with this. So here it says there's a sample of 106 body temperatures having a mean of 98.2 degrees with a standard deviation of 0.62 degrees. We're to construct a 95% confidence interval estimate for the whole population. Okay, so, and then there's a follow-up question. So here it doesn't say anything about it being normally distributed, but there's 106 temperatures, which is way more than 30, so that's fine. The 0.62 is a sample standard deviation. So we have no sigma, so we're going to use the t-distribution. So as before, we'll make a little sketch to help us get the t alpha over 2. We wanted a 95% confidence interval. our degrees of freedom here is going to be 105. So we'll have to take a look at the table to find our cutoff. So you'll notice in here that our degrees of freedom of 105 is not in our table. We have 100, and then the next one up is going to be 200. There's a couple of ways that you can handle this. If this, our degrees of freedom were closer to the middle, if it was like 140, maybe 160, we might be justified in using the mean of the rows for 100 and 200. But the 105 is not too far past 100. So we're just going to go ahead and use 100 for this. It probably won't change our result very much. If you take a look at our t-table, the difference between 100 and 200 is not that great. In this one, we're going to be having a 95% confidence interval. So the two-tail area is 0.05. And so that will be the middle column. And so 1.964, 1.972, and 1.967 are all relatively close together. So you can try on your own the difference between these and see how, try each of these and see how much that affects the confidence interval that we obtain. I'm going to go ahead and use 100, row for 100 for this. We'll call it 1.964. If you do this on StatCrunch, you might get a little bit different answer. All right, so then for our margin of error, it will be 1.964 times our sample standard deviation, which was 0.62, divided by the square root of our sample size. So let's calculate that. Get 0.12. All right, so then we'll take our mean, which was 98.2, plus or minus 0.12. So the lower end is 98.08, and our upper end is 98.32. All right, so there was our 95% confidence interval. The follow-up question says, what does this result suggest about the common belief that 98.6 is the mean body temperature? Well, we're 90%, 95% confident that mu falls in this interval, and it's pretty far below 98.6 in a way. So to me, that suggests that the true mean is lower than 98.6. All right, last example. The sodium content in 16 breakfast cereals is measured, has a mean of 185.9 milligrams, standard deviation of 56.8 milligrams. So on this one, it's only 16, it's less than 30. We don't have any information about the parent population being normal or not, but we've got this QQ plot. We can take a look at that. It looks like the data mostly follow a straight line for this, and so we'll go ahead and treat this as if it were normal. We don't have sigma though, so we will be using T. Our degrees of freedom is going to be 15. So I'll start with a little picture. We want a 99% confidence interval. That means that between the two tails, we'll have 0.01 in the two tails. Okay, so then referring to our t-table, we have a degrees of freedom of 15, and the area in two tails is 0.01. So our cutoff will be 2.947. Okay, margin of error will be our T alpha over 2 times S over root n. Our T alpha over 2 was 2.947. The standard deviation of the sample, 56.8 milligrams. And then our sample size was 16. So we'll calculate that. So that's 41.85. Okay, the mean was 185.9. So let's go ahead and finish by adding and subtracting that margin of error to and from our mean. So we'll have 144.05 up to 227.75. So you'll notice on this that our confidence interval is pretty wide. In a way, it runs from 144 up to 227. As an exercise for you, if you feel like it, figure out what a 90% confidence interval would be. Would it be narrower or would it be wider? So that are some things to think about. That takes us to the end of section 7.2. If you have any questions, let me know, and have a great day.